Alrighty, so welcome to this video on the Cholesky factorization. So in this video, we're going to specialize to only consider SPD matrices. So what I mean by this is that our matrices A, they need to satisfy the property that they are symmetric, so that their transpose equals themselves, but then also that they're positive definite. And so if you remember the definition that we had for a positive definite matrix, our definition was that for any non-zero vector x, a positive definite matrix by definition will satisfy this x transpose AX. This kind of triple product has to be greater than 0. It has to be strictly greater than 0. And so this is kind of a more special setting than what we've been talking about recently with Gaussian elimination, because for there you can have any invertible square matrix A. But when we talk about the Cholesky factorization, we really have to limit ourselves to only be considering kind of the subclass of invertible matrices that are symmetric positive definite. Recall that an SPD matrix is always invertible because it comes from this fact. And so kind of one interesting thing that happens is that it's possible to show that if A is an SPD matrix, that then actually you don't actually require any pivoting when you try to compute, say, an LU factorization via Gaussian elimination. It turns out that for SPD matrices, this Gaussian elimination method that we talked about is stable, and that you'll get an accurate result as long as your matrix isn't too ill-conditioned. And so how can you kind of arrive at the Cholesky factorization from the LU decomposition? So kind of one thing that you can notice is that say that I go ahead and I compute a Cholesky factor, or a LU factorization, sorry, of an SPD matrix A. And I've mentioned a couple times that you can always rewrite this as, say, a LDU factorization, where D is a diagonal matrix, and you wind up with this U tilde. It's a slightly rescaled version of the original matrix U that you would have in LU, in the LU factor. Kind of the purpose of doing this, or one purpose perhaps, could be in the LU decomposition, L has a unit diagonal, which means all of its diagonal entries are 1, but U does not. So it's not, I'll say, not unit diagonal. And so one way that you can kind of symmetrize this in a way is to come up with this scaling matrix D, it's a diagonal matrix, such that I can write A as the product of a unit lower triangular matrix times a diagonal matrix, which doesn't have to have 1s on it. It could be generally anything positive. And then this U tilde is has a unit diagonal now. It's an upper triangular matrix with a unit diagonal. So kind of you can think of this as a way, this LDU is a slightly different version of just the LU factorization. You can always get one from the other. It's just kind of a what is your goal? So, but for us, it's actually going to be important that we can do this because we're going to take advantage of this to basically arrive at the Cholesky decomposition. So what is my next step to kind of get to the Cholesky decomposition? By the way, I should probably say that what I'm trying to arrive at is I want to write A as the product of a lower triangular matrix. I'll call it maybe L prime, and the same lower triangular matrix but transposed. All right, so that's kind of my goal, so I'm going to circle that. That's called the Cholesky decomposition. Right, so I can take an SPD matrix and factorize as a lower triangular matrix times the same lower triangular matrix transposed. But how could I get there from just the LDU factorization? Well, since I know that A has to be equal to A transpose, kind of just inserting our LDU factorization, we know that this has to give us this U tilde transpose D L transpose. Remember, this D is diagonal, so it's symmetric. And this has to be equal to LDU, is what that would tell us. But one thing that we know is that these the LU factors and the LDU factors, they'll wind up being unique for our purposes. So, and the other thing we can note is that here, the transpose of an upper triangular matrix is a lower triangular matrix, right? And here, So I'll write this is lower triangle, lower T. But then the transpose of a lower triangular matrix is upper triangular, right? So this, we get an upper triangular matrix here. But if these two things are equal, right? So I have a lower triangular matrix times the diagonal times the upper triangular. And on the right-hand side, I get a lower triangular matrix times the diagonal times the upper triangular. Essentially, the conclusion that we can draw by this uniqueness argument is that actually this lower triangular matrix U tilde transpose has to be equal to L. And also that this L transpose matrix has to be equal to U. And so this is essentially how we arrive at the Cholesky decomposition. I just realized I kind of went out of frame. Put that back a little bit. So how do we kind of get to the last step? So let me erase this, because we're not quite there yet. So the last step is, so we know that A is now equal to LDL transpose. And since we have an SPD matrix, we know that this D matrix, the diagonal matrix D, has to have strictly positive diagonal entries. So because of this, we can always write this as, all right, L D1/2 times, and I'm going to run off the screen again, times essentially the same thing, L D1/2. Right, and so what do you think I'm going to do? I'm going to call this L prime. I'm going to call this L prime transpose. Right, so essentially we have to take the scaling from the diagonal matrix and kind of hit it with the L that we get out of the LU decomposition. And it turns out that we've arrived essentially at our target, which was A is equal to lower triangular times the same lower triangular transposed type of decomposition. So kind of to reiterate this point, what have we just argued? Well, so if I have an SPD matrix A, so I've just rewritten the definition up here for us. I have an SPD matrix A. Does there always exist, this is the question, does there always exist a lower triangular matrix L such that LL transpose is equal to A? And so the answer to this question, I guess you can make an argument, I didn't prove this to you, but Gaussian elimination applied to a SPD matrix will require no pivoting, in the sense that you'll never run into a zero pivot. So what this means is that the A equals LU decomposition will always exist for an SPD matrix, and then so will this A equals LD U tilde. So basically what I'm saying is you can always play this game that we just did to basically extract what was the L showing up here in the Cholesky decomposition, because the fact that you never require pivoting, right? So you don't have to worry that you might have needed to write, say, PA is equal to LU, or say PAQ is equal to LU if you were doing Gaussian elimination with partial pivoting or Gaussian elimination with complete pivoting, all right? So yes, so the answer kind of from that kind of argument is yes. But in this video, we're actually going to prove, give you an inductive proof for why the Cholesky factorization always exists. And kind of from the inductive proof, we're also going to get an algorithm for how you could compute it. And the algorithm here is going to actually be, you're going to arrive at it in a much different way than we did for Gaussian elimination, right? So Gaussian elimination, we came up with this sequence of these elementary lower triangular matrices. So I would pre-multiply A by some sequence of these elementary lower triangular matrices, and this would give us an upper triangular matrix U. But this is kind of a completely different type of factorization in the sense that we don't have to think about it in terms of these multiplying these elementary matrices. We're going to get kind of a nice inductive proof that's going to tell us how do we compute it step by step. So before we dive into the proof, I'm going to give you a little bit of history about the Cholesky decomposition, the Cholesky factorization. So in 1907, Toeplitz proved that for any SPD matrix A, that it could always be written as the product of a lower triangular matrix times the same lower triangular matrix transposed. But Toeplitz didn't give an algorithm for how this could be done. So this is why it's called the Cholesky algorithm, Cholesky factorization, because this is due to André Louis Cholesky. He was an army officer in the French Army Geographic Service, and what he worked on in the army was map triangulations via least squares. So what he was thinking a lot about was kind of given different measurements of distances between points, I'm trying to make a map, or I'm trying to accurately kind of figure out what are the exact distances of these points in relation to each other. And this can be formulated as a least squares problem. So this was kind of his interest in these types of matrix factorizations. Right, so there's evidence that Cholesky had developed this in 1902 to 1904. There was an unpublished manuscript that was found in 1910 that detailed the method, but wasn't actually published by Cholesky even during his lifetime. It was published later by a friend in 1924. So this is really when it first kind of entered the record, but there's kind of evidence that he had been working on it well before. Yeah, and then kind of the other interesting fact is that comparing this to Gaussian elimination, and we talked about all these different types of factorizations, is that Cholesky actually predates all of these, right? So I had mentioned in that video that Banashevich in 1938 had pointed out, people had been using Gaussian elimination for a long time, but he pointed out that, hey, actually this process is generating an L and a U factorization, or an LDU factorization, through the process of Gaussian elimination. So Banashevich actually explicitly pointed out in 1938, yet Cholesky, in a kind of well before that, had said, Cholesky had always been thinking of it in terms of a matrix decomposition from the start, right? So in that sense, you could say that Cholesky predates these LU or these LDU factorizations that we've been talking about. Okay, so before we actually get into the proof of the existence of the Cholesky factorization, we kind of need a lemma that's going to help us along the way. And so what this lemma says, so let me kind of give you a definition, is that I'm going to let this A sub k denote the leading principal submatrix of order k of an SPD matrix A. Right, so what do I mean by that? So if I have an SPD matrix A, so say that A has to be SPD, what I'm going to do is I'm going to write it in block form like this. So here I'll just kind of block it off as these different blocks. And so this upper left block of size k by k, right? So this is k, this is k. And then there might be some other things here, like so there's going to be some yk block, some zk block. I think you get the picture, right? And this would have to be the transpose of the other yk. Right, so all this AK is it's saying, hey, take the first k rows and columns, take that matrix that's formed by those, and consider it separately, right? And so what is this lemma, or what is this proposition that we're going to have to use when we prove the existence of the Cholesky decomposition? So this proposition, all it says is that if A was SPD to begin with, then this leading principal submatrix is also SPD for any of the k's, right? So k could be between 1 to n. It could be the first 1 by 1 block, which is just the upper left entry, but it could also be the entire matrix or anything in between, right? As long as it's a square submatrix starting in the upper left corner. Right, so how do we prove this? There's going to be two ways. There's going to be one, I'm going to give you a direct proof. And then there's going to be a second proof where you can just kind of invoke a theorem about eigenvalues to also tell you why this has to be true. So I'm going to show you both of them. So how can we prove this proposition directly? So we're actually going to do a proof by contradiction. Right? And so the idea of these proofs by contradiction is that we're going to assume that the thing we're trying to prove is not true, and then find why it would have to contradict some other fact that we know is already true. Right? So our contradiction is we're going to say, suppose there is some x in Rk with x not the zero vector, so it can't just be the zero vector, such that that triple product x transpose a k x is less or equal to 0, right? So I'm trying to show that this actually has to be always greater than 0, which means it would be SPD. But I'm going to assume actually that it's not, that it's something equal to 0 or less than 0. And we're going to try to find a contradiction. So the thing we're going to consider, so I'm going to say consider, I'm going to call the zero padded matrix, zero padded vector. Called zero padded vector. We call it x tilde, where I get this x tilde by taking x, so this x that I'm supposing exists, and I'm stacking a block of just another zero vector of length n minus k below it. Right? So what I'm doing is I'm building a vector that's of length n, which is the size of the original matrix, out of this this vector that's only of length k. And I'm just zero padding it to get there. But then what I'm going to do is I'm going to consider this triple product in terms of x tilde in the original matrix A. Right? So this x tilde transpose A x tilde. Well, what is this equal to? This is going to be equal to x transpose the 0 transposed. And kind of in terms of that block notation, we're going to have AK in the upper left block. We're going to have some YK transpose and some YK in the top right block and the bottom left block. And then there's also some ZK. We don't actually care what these things are because they're going to disappear in the proof. Right, so I'm just letting this denote whatever those blocks, whatever entries are in those blocks. All right, and then I'll get x and 0 there. All right, and then what happens is that we can see that this is equal to x transpose 0 transpose. We just multiply out that first matrix vector product, and we're going to get AK x followed by YK transpose x. And if we go one more step, you'll see that this is actually just equal to x transpose AXK x. Right? But we know what? So we know that A itself is SPD. So whatever this is has to be greater than 0. But in our assumption, we assumed that we've arrived at this term that showed up in our assumption, right? So our assumption was x transpose AKX. We assumed that this was less than or equal to 0. So that's the contradiction, right? So we assumed that there was a vector that could make this triple product 0 or negative. And then we showed why that would mean that there has to be a vector that makes the larger matrix that we already know is SPD, not SPD, right? So that's the proof, right? We have therefore a contradiction because both of these things could not be true. Right, so next I'm going to give you kind of a shorter proof just invoking a classic theorem about eigenvalues. So there's actually an easier proof, or an alternative proof, to why the leading principal submatrices of SPD matrices must also be SPD. And kind of this other proof relies on kind of just invoking a classical theorem about eigenvalues known as the Cauchy interlacing theorem. So what does the Cauchy interlacing theorem state? So if I have an SPD matrix A, this interlacing theorem doesn't require that A is SPD, it just happens to be in our case. The theorem actually only requires that A is symmetric. But if I have a symmetric matrix A, and I have a matrix, I'm going to call it AK, which is what we're talking about, these leading principal submatrices of dimension k by k. Remember, the A itself is dimension n by n. So what Cauchy's interlacing theorem says is that the eigenvalues, so if I look at the ith eigenvalue of AK, the interlacing theorem states that this eigenvalue has to live between, so it has to be upper bounded by the ith eigenvalue of A, or the whole matrix that's kind of encompassing AK, but then also it has to be bounded below by another eigenvalue related to A, and that eigenvalue is equal to the lambda I plus n minus k eigenvalue of A. And this is valid for I equals 1 all the way to k, right? Because AK is a k by k matrix and has k eigenvalues. So that's the Cauchy interlacing theorem, and that's what it states. So here I have a kind of visual representation of what this means. So what I've done here is I've taken a 10 by 10 SPD matrix, and I've just plotted its eigenvalues for each of the successive submatrices. So here, this is the A1, which only has one eigenvalue, right? And so it happened to be that blue dot. And what you'll notice is that when I move over to A2, that single eigenvalue interlaces the two eigenvalues of A2, right? And then you'll see the same pattern emerge as I go to A3 or to A4 or to A5, is that when I look at each successive matrix, the eigenvalues all interlace exactly the eigenvalues from the previous submatrix. And this will go all the way down to AN, which is equal to A, right? So why does this prove that all leading principal submatrices of SPD matrices are themselves SPD? Well, if you note, so pretend that A10 was A, so say that N was 10, and so say that these were all the eigenvalues. And so if all of the eigenvalues were positive, so in this case they weren't, so actually I meant to say that A here was, the A that I made for this plot was symmetric but not positive definite. But if all of the eigenvalues had been positive, then you can see that a lower bound on the eigenvalue is given by the smallest eigenvalue of A10, or the large encompassing matrix A. And so what that tells you is that any of these submatrices can't have an eigen. If the original matrix doesn't have an eigenvalue of 0 or less, then neither could any of these submatrices, right? So the A9, the A8, the A7, because they all interlace the eigenvalues of the larger matrix. So there's your simple proof using the Cauchy interlacing theorem, why all leading principal submatrices of an SPD matrix are also SPD themselves. So next we're going to dig into the main proof of this video, which is the proof of the existence of the Cholesky factorization for an SPD matrix A. Right, and so our proof strategy here is going to be a proof by induction. So this is why we warmed up with proof by induction during the first week of the class, just so that we could do proofs like this later on. And so what would the base case be for proving that the Cholesky decomposition exists for SPD matrices? I'm going to consider the case k equals 1. And what I'm going to do here is I'm going to consider that that leading principal submatrix A1. Right, so here, this A1 is going to be just the 1-by-1 matrix formed by just taking the upper left corner entry of A, right, because that's the first leading principal submatrix. And note that this is just a scalar, but I can view it as a 1-by-1 matrix. Then what I'm going to do is I can write this as, just by taking a square root. Why can I take a square root? It's because of that proposition, that lemma that we just talked about. Right, so I know that A11 has to be positive because it's a leading principal submatrix, right? And so it has to be SPD, which for the scalar case means that it's positive. So here I would say this would look like, I'll call it A11 to the 1/2 times, I'm going to write A11 to the 1/2 transpose. So because it's a scalar, the transpose doesn't really matter, right? So I can write it. And so what I'm going to call these is I'm going to call this, define this as being L1, and then this one would be the transpose of L1. Right, so kind of what's happening here is that for the base case, we've shown that we can take A1, which is the first principal submatrix, and we've shown that we basically have argued the existence of the Cholesky factor for the 1-by-1 submatrix, right? So that establishes our base case So what would be the inductive hypothesis, right, for our proof by induction? What we're going to do is we're going to assume that we can always Cholesky factorize the A-kth leading principal submatrix, right? So assume that AK is equal to LK transpose for some lower triangular matrix. LK is in K by K, right? Because that's the dimension of LK. So we're going to assume that we're able to do it for some K. And then what we're going to do for the next step of induction is we're going to show that given that assumption, we can always construct a lower triangular factor for the Cholesky factorization of the next one, right? So we're going to prove why we can always Cholesky factorize AK plus 1, given the fact that we can Cholesky factorize AK, right? And so there's a claim. First, let me write down kind of our goal, right? So we're going to take AK plus 1, and I'm just going to note that we can write this in a block form, right, as AK in the upper left block, right, just by definition of these leading principal submatrices. And then you're going to have D transpose gamma. And so what are these D's and these gammas? I'm just using this as a generic notation for whenever I enlarge AK by one row and one column, the D in the gamma, so D is a vector and gamma is a scalar. D is just whatever column ends up being in that enlarged matrix, right? So I'm just saying D would be the very last column of AK plus 1, the new column, except the last entry, right? And then I'm using gamma to denote the last entry in that column. And then because it's symmetric, we know that this other row, the new row, has to look like the transpose of D. Right, so this is just some notation for these generic extra vectors and scalars that I've added. Right, and so kind of how does the rest of the proof go before I move on to the next slide? So I'm going to make a claim. So my claim is that for any AK and for any D and gamma that make AK plus 1 still SPD, there always exists some vector R in RK and some row with positive such that AK plus 1 is equal to the product of LK R transpose 0 row times the transpose of this matrix. So LK R transpose row 0 transpose. So, and by the way, I noticed that you can't see that, so let me kind of move it up for you right here. So this is my claim. So note that if we could prove that for any AK, D, and gamma, that there always exists such a vector R and a scalar row greater than 0, if we could prove that these existed, then we're done with the inductive proof, right? Because why? This would be our Cholesky factor for the AK plus 1 leading principal submatrix, right? Because it is itself lower triangular, and we've constructed it by taking the previous Cholesky factor for AK and then stacking below it this R transpose in this row, right? So this vector and this scalar that we're claiming exists, right? And so to actually prove, right, so this would be LK plus 1, by the way, and this would be LK plus 1 transpose. So if we could prove that this vector R and row exist, then we're done with the proof, right? But we have to make sure that the R always exists and that the row always exists and is positive. It's a positive real number. So that will take us to the next slide. So how can we prove that this R and this row always exists? So what we're going to do is we're going to play a quick matching game. So what I mean by this matching game is that what I want to do is I want to take AK plus 1, which, by the way, I know that I can write in this block form as AK D transpose rho. What I want to do is I want to find this R in this row such that I can write AK plus 1 as LK R transpose rho 0 times LK transpose R 0 rho. But if this was true, or if I had found such an R in such a row, if I multiplied this out, so what would I get if I multiplied these two matrices? I would get LK transpose. And note that this is just AK, right? Because we've, by the inductive hypothesis, you would get LKR. You would get R transpose LK transpose. And then you would get, in the bottom right corner, you get R transpose R plus rho squared. So if this was true, or if such a R and such a rho existed, what would have to be true is that you'd have to have an entry-wise equality, right, between these two matrices. So what would have to be satisfied? So you're already taken care of for the LK transpose and the AK. So the upper left one's already fine. But we're going to get two more equalities out of this. So the first one is going to be that D has to be equal to LKR. And the second one is going to be that rho, and sorry, I just realized that this rho here is supposed to be a gamma, right? So the next one is that gamma is equal to R transpose R plus rho squared. Right, so we have kind of a system of two equations. We have two unknowns, right? We have one that's a vector and one that's a scalar, but this is actually enough to determine the solution. Right, so what can we do to the first one? Well, because AK was SPD, right, by that lemma, that proposition that we proved, we know that it's always invertible, and you can argue why this means that its Cholesky factor also has to be invertible, right? So its Cholesky factor is, in this case, is LK. So we know that we're always justified to take the inverse here. So this would mean that R is equal to LK inverse D. So how do you get R? Right. So when I add my next row or my next column to the matrix going from AK to AK plus 1, what I'm going to do is take that. I'm going to take that new column, except the very last entry, right, which was gamma, and then I'm just going to apply the inverse of my Cholesky factor to it, and that's going to be my vector R. Right. So once I've done that, how can I use that now to figure out what rho is? Well, by this equation, we know that rho squared is equal to gamma minus R transpose R, right? We can take the square root. So this will give us rho is equal to plus or minus the square root of gamma minus R transpose R. And you can just pick one. Let's pick the positive one. Okay, so, right. So there's kind of one last question we have to ask, right? So we know that we're always justified to do this, but one thing that we were not quite sure about is, does this have to be greater than or equal to 0? Right? Really, we want it to be greater than 0 because we need, it would just have to be greater than 0, right? So how do we justify that this quantity gamma minus R transpose R is positive? So that will take us to the next slide. Okay, so let's address why this, right? So we had that rho was equal to plus or minus the square root of gamma minus R transpose R, and we want to address why is this inside quantity positive, right? Because that means we can take the square root and we don't have to worry about complex numbers, right? Because we want the Cholesky factor to be a real valued, or have real entries, real valued entries. So why is this greater than 0? We can prove why this has to be the case by using the SPD property of AK. So what I mean by this is I'm going to pick a choice, right? Because we know that for any x we know that x transpose AX has to be greater than 0. And then we also know that, I mean, if I resize x to be something of length k, we know that this would have to be true for any of the submatrices, right? That's by our that lemma, or that proposition we showed earlier. So how can we use this fact? I'm going to make a specific choice of x. Okay, so this choice that I'm going to make, I'm kind of choosing this in advance because I know this will work out to give me the result I want. But otherwise, it kind of seems almost magical of how I knew to pick this. I'm going to pick the vector R transpose LK inverse. So that vector, and then -1, followed by just a single entry of -1, times AK plus 1. And then, right, because this is my X transpose, I'm going to just take the same vector and then put it up here, transpose. So LK minus transpose, which is just the inverse, and then transpose the inverse, R. And I'll get -1, a single entry of -1 right there. Right, so I made this choice, and then what do I know has to be true? I know that this has to be greater than 0. Right, because AK plus 1 is positive definite. So we know automatically that this triple product will have to be positive. Well, let's go ahead and multiply it out and see what this tells us. So if I start multiplying this out, what I'm going to get is, you'll see that you go R transpose LK inverse -1. If I use that block form of AK plus 1 that we had before, and then we do the matrix vector product, what we're going to get is we're going to get AK LK minus transpose R minus D, all in one row. Right, so there's the first row looks like that, and then the second row looks like D transpose LK minus T R minus gamma. That's the second row. Right, and so then we're just going to continue this dot product here, and we're going to arrive at this kind of long expression. So it's going to be R transpose LK inverse AK LK minus transpose R minus R transpose LK inverse D minus D transpose LK minus transpose R plus gamma. Okay, so that's what we're going to end up with. And then we can simplify a little bit, right? Because what do we know? We know that AK is equal to LK times LK transpose. So what we'll see is that actually this whole thing will annihilate to the identity. Right? So we're going to get R transpose R. And remember that actually LK inverse D was equal to R. Right? So we can use that to take care of these two terms. So we're going to wind up with R transpose R minus R transpose R, again minus R transpose R, plus gamma. Right, and so what will this do is we're going to wind up with a final sum of gamma minus R transpose R. Right, and so remember what we said at the very beginning. We already know that whatever this result is, that it has to be positive. So we know that kind of therefore gamma minus R transpose R has to be positive, right? So this all kind of relied on me making a special choice of kind of what is the X transpose AK plus 1X that I'm looking at. But once I made that choice, we were able to show why, because AK plus 1 is positive definite, then that would imply that this gamma minus R transpose R has to be a positive number, which means that we're justified in this choice of row. Right, so this row will always be a real number, which is what we want. Right, so I'm going to summarize this on the next slide. Right, so we just showed that this choice of R, this vector R in the scalar row, was always well defined. And so what this means is that given that inductive hypothesis, that we could always Cholesky factorize AK, we know that there always exists this R in this row such that AK plus 1 can be factorized as LK 0 R transpose rho times the transpose of that same matrix. So LK R transpose rho 0 transpose. And we're going to call this this is going to be LK plus 1, and this is going to be LK plus 1 transpose. Right, so we're good to go. So we've proven that you can always then Cholesky factorize the next leading principal submatrix, and so that's how the inductive proof goes, right? So therefore, by induction, such factorization exists for k between 1 and n. Right? We don't go off to infinity because we have a finite dimensional matrix, right? It terminates at n. Right? So that's your proof by for the existence of the Cholesky factorization for an SPD matrix A. So I wanted to give you some quick theory on whether or not we can trust this Cholesky factorization algorithm. And I didn't explicitly go over the algorithm in this video, but it's pretty easy to see how you could come up with it from the inductive proof. Right? So you can always build the next Cholesky factor given the previous one, and you can build an algorithm out of that. But I want to ask, can we trust the computed Cholesky factor that we get out of this method? And so there's kind of three results I'm going to go over. So the first one is this theorem by Demel in 1989. And so this theorem, what it says is that the Cholesky method will produce some computed tilde L, such that when I multiply out the Cholesky factors, right, so that's this L tilde transpose, when I multiply it out, I'm going to get the thing I want plus some error matrix. And the elements of this error matrix have to satisfy this kind of error bound, right? And so one thing you'll notice is that this is bounded by something in terms of machine precision, and then also the actual components of the matrix A that I tried to factorize. So that's kind of your, I'd say, your forward error result, or your bound on what that could look like for the problem of computing the Cholesky factor, right? So I'm not talking about for computing solving a linear system given the computed Cholesky factor. This is just for putting bounds on the error in the computed factor itself. And so what this next theorem says is actually talking about solving linear systems. Right? So it says, what this theorem says is that if I take Ax equals b, where A is SPD, and I solve it using this Cholesky method, it's going to give me a computed tilde x. And what's going to be true about this tilde x is that it satisfies some exact equation with a perturbed matrix, right? So this is like your backwards error result, like we talked about earlier in the class, right? So it's what is the perturbed input for which the solution is exact. So what's true about this error matrix now is that you can bound its 2 norm by some small constant times the machine epsilon times the 2 norm of A. Right, so unlike this other expression, which was an element-wise, absolute value element-wise statement, here we get something in terms of the 2 norm of A. Right, so this basically tells you that yes, Cholesky is a backward stable method for the purpose of computing solutions to linear systems with SPD matrices A. Right, you can also get this other kind of relative error bound. Right, so if I want to ask how far away relatively can that x tilde be from the true solution, which would be x, well, I know that the relative error has to be bounded above by machine epsilon times the condition number of A, this is pretty much as good as you can hope for. So if you remember when we talked about accuracy, stability, those types of things earlier in the class, remember that if I had a very ill-conditioned problem, I can't expect to get a highly accurate result, right? And here that's encoded in this kappa A, condition number of A. Right? So as long as that isn't too large, we know that we get a computed solution that's accurate basically to machine precision. for the Cholesky factorization. So the last thing I wanted to go over in this video is kind of a special topic for the purposes of this class. And so what I'm talking about here is, what if I relax this assumption that A has to be symmetric positive definite, and say instead only assuming that it's a symmetric and positive semidefinite matrix. So what I mean by that is that it's still going to be symmetric, so A transpose is equal to A. But when I look at this triple product for any non-zero vector x, I know that, or what I'm assuming only is that it's greater than or equal to 0. Right? So note that that's different than just saying it's greater than 0 strictly. And so this is why it's called semi-definite. Right? So if it could be 0, if I'm not assuming that it must be strictly greater than 0, then it goes from being positive definite to now only positive semi-definite. Right, so I'm worried about when A has now possibly some 0 eigenvalues. Right? That would be the equivalent kind of statement. So the question is, can we modify the Cholesky algorithm to still work in this case? So if you just take a positive semi-definite matrix, symmetric positive semi-definite matrix A, and you apply the Cholesky algorithm to it, it will fail at some point, unless it was a very special matrix. So in general, it will fail for these matrices. And so we want to know, is there a way to somehow modify the algorithm slightly so that we don't fail, but we get something that's of a very similar form? All right. So here, what I'm going to ask for is not that A is equal to L transpose, but that maybe there's some permutation matrix P where P transpose AP is equal to L transpose. Right. So I'm gonna say, kind of change the target a little bit and ask, can I achieve this? And so the answer is yes, you can do this. So here's a theorem that I'll quote for you. So what the theorem says is, let A be, so here's, I'm using SPS. Sorry, this should be a D, right? Symmetric positive semi-definite. So I'm going to let A be symmetric positive semi-definite with the rank of A being this quantity R, and I'm assuming that it's less than n, right? So I'm basically assuming that it's not, A does not have full rank, which means that it does have at least a couple 0 eigenvalues. The number of 0 eigenvalues would be equal to n minus R in this case. So what this theorem says is that then there has to exist some permutation matrix P, orthogonal permutation matrix, such that I can express P transpose AP as being equal to some lower triangular Cholesky factors like we've had before. But the difference is that this L, you can always write it in this block form, or it would always exist so that you could write it like this, where I have an upper left block that's of size R by R. I have some rectangular block below that's going to be of size n minus R by R. And then finally, it's followed by some block of zeros of shape n minus R by R. So, right, so what does this tell you is that, yes, the Cholesky factorization will still exist. So let me maybe draw this triangle. But once you get to some point, you're going to have essentially a block of zeros off to the right. So, and that will also mean, that the L is not invertible, because on its diagonal it will have some zeros. So that's what we'd expect, because A itself is not invertible if it has 0 eigenvalues, right? So on the next slide, I'm going to kind of give you an idea of how you could do this, or how you could modify the algorithm to give you this type of factorization. So what is the idea for how you could modify the Cholesky algorithm, or the Cholesky factorization, to accommodate these permutations that allow you to still factorize A as being P transpose AP being equal to, let me write that a little more cleanly, P transpose AP as being equal to L transpose for some L and for some P. So the idea is, maybe I go through the kth step. So remember our inductive proof. Say that I'm in my kth step, or k plus 1 step, and so I've already Cholesky factorized the previous block successfully. But what will happen when I have some 0 eigenvalues is that eventually, when I try to do the next step, so I'm in step k plus 1, so I've added this new column and this new entry and this new row vector to A. What will happen is that I'll do my calculation out, right? So I'll compute the R in the new Cholesky factor as being LK inverse D, and I'll compute this row like we talked about. But what's going to happen is that that row will end up being 0, right? So maybe row becomes 0 eventually because I do have these 0 eigenvalues. So the idea is instead of then accepting, or why is this a problem, right? So this is a problem because if I accept row as being 0, then what happens is that I have a look in the k plus 1 step, I've generated an LK plus 1 that looks like kind of all maybe possibly dense, but then it has that last corner is 0, which means that LK plus 1 is not invertible, right? Because it has a 0 on its diagonal now. And so then when I went to go do the kind of step k plus 2, the matrix that would show up when I compute with R would be LK plus 1 inverse, which does not exist, right? So this is why we can't allow row to be 0, at least for most of the algorithm, right? So how do we kind of fix this problem? The way that we do it is we try to permute away that row and kind of push it to the end, right? So say that I do this process and I get that row is 0. What I'm going to do is not accept this as my Cholesky factorization of AK plus 1. What I'm going to do is I'm going to say, hey, when I look at this, let me draw another diagram. So, right, so I did, maybe here's what AK looks like, and then here's the new row in the k plus 1 step in the new column. What I'm going to do is say, hey, let me draw this all the way up. I'm going to say, okay, because I got a 0 here when or because I got row being 0 in that new Cholesky factor, I'm going to say, hey, take this whole column and just permute it away, maybe to the very end. Right? And then because it's symmetric, I have to say, hey, take this whole row and permute it away to the very end. And then I'm going to take whatever row was there and whatever column was there and bring it into the position of this row, or this column in this row. And so the hope then is that with that the fact that now that I'm dealing with a different column and a different row, that then row, the variable row, will not end up being 0 in that step, right? And so eventually what happens is that if I keep doing this process and I keep kind of shoving these columns and rows off to the very end, eventually there'll become a point where there are no, if I try to keep shoving these away and bringing in a new row and a new column that would make the row not 0, the idea is eventually you'll have run out of columns and rows to actually do this with, right? And in that case, what's exactly happened is that you've produced an L such that you have an L11 it's a R by R matrix. The other thing I should point out is that it has strictly positive diagonal entries, as long as we'd always made the positive choice, right? When we computed row, you'll have some L21 down below, and then you'll have a block of 0 off to the lower right, and kind of this is collecting the information of those columns and those rows that we had permuted away to the very end, right? So we terminate the algorithm once there are no more columns and rows that we can bring in to try to make the row here that we would compute in that factor not 0, right? So eventually you've run out of columns and rows because you only have n of them, right? And it will turn out you could prove that the number of ones that you will succeed for, there's exactly R of them, which is the number of non-zero eigenvalues. that's kind of your quick introduction to the Cholesky factorization, why it always exists for SPD matrices A, as well as how can you modify it, kind of for bonus for this class. We're not going to emphasize it that much. How can I modify it so that it can still work when I have rank deficiency in my SPD matrix, which then makes it an SPSD matrix, symmetric, positive, semi-definite.